Good morning dear students, welcome back. I am your physics teacher Dr. Nagaraj explaining quantum computation. It is part of engineering physics syllabus VTU. So far I explained up to multi-qubit gate, one multi-qubit gate that is called CCNOT gate I have explained. In CCNOT gate we have what is called control qubit and target qubit. Control qubit is mentioned by its solid dot and target is represented by plus. See, this is the circuit symbol. So we have a control qubit over here and we have a target over here. Target looks like plus mark, and control will always act on the target. Whether it acts or not, the input will come out without any problem. So that is the output. Whereas target B will come out with some alterations because of the operation of A on B. Remember, we are talking about multi-qubits. Multi-qubit, one example, I write it as AB, where A is considered as control, B is considered as target. If you take 0, 0, then it comes out without any problem, without any change. So this first 0 is control, next 0 is target. It is just a small revision before I proceed with the next gate. All these details are available in my previous video. Please go through it once again. So the next gate comes, it is a swap gate. Dear students, remember we are talking about multi-qubits, 2-qubit system. See, in 2-qubit system, sometimes we need to change one state to another state. Say for example here, this is control. Control is represented like this. I need to change control to target, control to target, target to control. I want to make A to B, B to A. It all depends on my requirement. When it comes to quantum algorithm, I may need this situation. So therefore I should have one such gate which can swap the control and target. The control should become target, target should become control. So that is the swap gate purpose. See, it is like this. I have 0 as control, I have 1 as target. So 0 should become 1, 1 should become 0. Or I have 1 as control, 0 as target. Same thing, 1 should become 0, 0 should become 1. See, remember always top represents control. So 1 is control, this is the top line. 0 is target. Okay, so swapping means 1 should become target, 0 should become control. So 0 should go to control level, 1 should go to target level. So this is the main purpose of swap gate. How it is done? So it is nothing but continuation of CCNOT gate. See, this is my CCNOT gate. CCNOT gate continuation is swap gate. Actually, swap gate consists of many CCNOT gates. Then only control and target can be swapped. I will explain this only with the help of circuit diagram or the symbolic representation of the CCNOT gate. See, swap gate is nothing but a gate which changes control to target, target to control. This is the definition. That's all. Control becomes target, target becomes control. How it is done? See, it is like this. First, I have one CCNOT gate. So this is the circuit symbol of CCNOT gate. Okay. So I take this one only, this example only. I take 1 as control, 0 as target. Dear students, you all know when the control gate will work? Only when the control is in ket1 state. It will act. How it will act? It acts like police X gate. It acts like police X gate. Okay. So now 1 is going to act. Act or not? Yes sir, it will act because it is in ket1 state. So it will change the state of 0. So 0 will now become 1. Okay. So flip. This is called bit flip. So that is X operation. What about 1? I already told you whether control operates on target or no operation on the target, it will come out unaffected. So 1 will come out unaffected. So my input was 1 0, output is 1 1. This is just one CCNOT gate. This is one CCNOT gate. What I will do, I extend this further and I put one more CCNOT gate ulta. Now reverse I put. That means I take this as control and I make this as target. So this is my reverse control gate. Okay. now what happens? Okay, now look at this. This is the control. Control is 1. Control 1 will come out without any problem. Control will come without any problem, but it will act on the target. What is target now? Target is ket 1. So control, andre whatever the process happened here, the opposite is happening here. So control 1, control gate is in ket 1. Whenever control is in ket 1, it should act. Yes, it will act. On whom it will act? It will act on target. How it will act? It will act like police matrix. So X matrix, sorry. So 1 now should become 0. So look at this. Earlier I had 1 in the control level. It is now in the target level. Earlier I had 0 in the target level. Now it is in the control level. So 1, that's what 1 is now here, flip, and 0 is now here. So look at this. This is a swap gate. Swap gate consists of at least 3 CNOT gates. Sir, you have written only 2. Just to explain this 1 0, I have written. That means 1 0 multi-qubit finally is going to become 0 1. Correct? So 1 0 is going to become 0 1. So this is the flip. So for 1 0 to 0 1, 2 control enough. But it is not possible to achieve same thing for all the states. Therefore, it is better to have many CNOT gates. At least 3 CNOT gates, minimum 3 CNOT gates I need. So 3 CNOT gates I take. First, this is control, this is target, it acts on this. Next, this is control, this is target, acts on this. Next, this is control, this is target, acts on this. So how many is totally? 3. Now you write any of the possible states. You know already there are 4 states. They are ket 0 0, ket 0 1, ket 1 0, ket 1 1. Okay, so these things, what will happen? Let us see. Ket 0 0, that means this is control. Only one I will show you. This is control 0, this is ket 0. That means target 0. So control is in the 0 state, it will not act. So 0 0 comes out without any problem, and this 0 0 also comes out without any problem. Similarly, this 0 will go without any problem, this also will come out without any problem, like that, like that. That means 0 0 is not flipped. 0 0 not flipped. Okay, then you think of the next one. Think of the next one. I will write it here only just by changing the symbols. I write it here only. Please follow carefully. What will happen in case of next one? Right, next one. So we came to know that this won't change, it remains 0 0. If the input is like this, output will be like this. If the input is like this, so ket 0 in the control level, ket 1 in the target level initially. So 0 is control, no effect, no action. So 0 comes out as it is, 1 comes out as it is. This is one control gate, one control gate. Now look at this one. Control is now in the 1 state, therefore it has to act. On whom? It acts on this fellow. This fellow will now become ket 1. This fellow will come out without any problem, without any problem. Okay, now this is going to be the control for the next one. So this control 1 will act on this fellow. So 1 becomes 0. This 1 comes out without any problem. So initially I had 0 1, finally I have 1 0. So 0 1 changes to 1 0. Did you understand? Okay, now try another one. So change the states. Third qubit I will write. Third qubit is 1 0. Just 1 minute. Third qubit is 1 0. 1 is in the control level, 0 is in the target level, 1 certainly will act on 0, 0 becomes 1 and 1 comes out without any change. Okay, then 1 goes to next, because it is control, it will come out without any problem, but acts on this, so it is 0. Correct? I hope you are following this. And now 0 is control, it won't act, so it comes out without any change, and this also will come without any change. So 1 0 becomes 0 1, 1 0 becomes 0 1. Correct? Now coming to the last one. Last one is 1 1 state. Let us see what happens. This is 1 1. Can you guess what will happen? 1 has to come here, 1 has to go there. That is what flip is. 1 has to come here, 1 has to go there. That means 1 1 remains 1 1 only. Let us see. 1 1. So first term is control, next term is target. 1 comes out without any problem. 1 will act on this one, so this becomes 0 initially. Now 0 will not act on 1, so this is 0 only. This is 1 only. Correct? No? 0 will not act on 1 because the control is in 0 state, therefore it won't act. Now this becomes control, it will certainly act on this fellow will now become 1, this fellow will come out without any problem. See, that's what I told you, 1 1 remains as it is. So this is 1 1. So this itself is the truth table. So just you remove the middle line, this you remove the line, okay, and then this is the truth table, input, output. Clear? Now, how to write the circuit? How to write the circuit? Just you have to draw 2 lines. Already told you this is a multi-qubit system, therefore there must be 2 lines. And one of them is a control. When control acts on the target, what will happen? Target won't remain as it is, it will change. How it will change? It will act like a police X gate, therefore I have written X. So it will flip, 1 becomes 0, 0 becomes 1. So this X I have written. So this is the circuit symbol of swap gate. I hope you got it. Now whenever I discuss gate, I have to explain 3 things. Number 1, circuit symbol. Number 2, operations. Number 3, truth table. But most important, the 4th one, actually I should mention it in the beginning itself, matrix form. Matrix form is very, very important. Why? Because I already told you quantum gate is nothing but an operation, matrix operation on our gate states, that is 0 or 0 0 or 1 0 or 1 1, like that. Qubits, it is acting on our qubits. So now the question, what is the matrix form of swap gate? So here comes the swap gate for matrix form. Swap is equal to, so it is nothing but 4 by 4 only. So first you write for 0 0, it is 1 1 0 0 0. This you know how to write, it is nothing but tensor product. Next line also you write 0 1 0 0. Next line also you write 0 0 1 0. Next line also you write 0 0 0 0 1. But this is not the matrix form. Dear students, please follow carefully. This is not the matrix form. I have written only the vector space of 0 0 1 1 0 1 1 ashtene. That's all, nothing else. Now look at the truth table. 0 0 no change, so don't change the first line. 1 1 no change, don't change the last line. Only the middle one. 0 1 is becoming 1 0, 1 0 becoming 0 1. That means this column should go there, that column should come here. So just you take this and put it there, take that, put it here. That means you have to swap like this. You have to swap like this. If you do so, what will happen? This one will come here, this one will come here, and this one will go here. So that this is 0, this is 0. Okay, so this is now what is called swap gate matrix form. Dear students, I will now give you small task. What task? Show that when swap acts on my 0 0, it remains as 0 0 only. It should remain as 0 0 only. Sir, how to do this? Already you know. Swap, you write the matrix form 1 0 0 0. Next 0 0 1 0. Next 0 1 0 0. Next 0 0 0 1. This is now operated on my 0 0 state 1 0 0 0. That's all. Okay. Now multiply and simplify. 1 into 1 1. plus 0 into 0 0, I won't write 0 into 0 0, 0 into 0 0, so it's totally 4 zeros. I simply write 1 0, but remember, because of shortage of space I am not writing remaining zeros, but it is not that only 2 elements, there are 4. Okay na? Now next 0 into 1 0, plus 0 into 0 0, plus 1 into 0, plus 0 into 0, so full zeros only. Next third row and first column, 0 into 1 0, plus 1 into 0 0, plus 0 into 0, plus 0 into 0, all zeros. Next last row, 0 into 1 0 into 1 0, next 0 into 0 0 into 0, 1 into 0, all are zeros. Okay na? Now look at this, it is nothing but, I write it here, it is nothing but 1 0 0 and 0, which is nothing but ket 0 0 only. So we proved this not only using the circuit action, even through the operation also. This is what the gate concept is. In circuit I have some component, in operation I have some matrix. Means in the matrix form I have some operations, in the circuit form I have some components. Components will take care of all these variations, and the same thing I prove through the operations also. So one task I solved, I give you remaining 2 tasks, this one, this one, this one. That means operate swap on 0 1, show that it remains 1, it becomes 1 0, and swap on 1 0, show that it becomes 0 1, show that it becomes 0 1, and swap on 1 1 does not make any changes. So these things you can expect as numerical problems in the test or in your internal test or in the main exams like that. So this is about the swap gate. I hope you followed this. Now I move on to the next gate. Dear students, what actually happening in swap gate, control qubit is acting on the target, producing the effect of X Pauli gate. That means it is a combination of CNOT and X gate. Swap gate is almost equivalent to combination of CNOT and X. That means CNOT can combine with X. Similarly, CNOT can combine with Y as well as Z. So CNOT, that is control NOT gate, which is meant for multi-qubit, can act on single qubit. Okay, so this is single. It means it acts like single qubit. This property we extend even for Z also, and that is nothing but CNOT Z gate. This is our next gate. It is control NOT Z gate. Definitely there will be control qubit. Next, in the next level, as I mentioned earlier here X, I should mention Z here. Okay. Now how it operates, how it works. I write again the same 0 0 0 1 1 0 and 1 1. Let us see what will happen. Input and output. Well, 0. Oh, okay. I draw the line here. I draw the line here. So this is ket 0, ket 0, ket 0. Sorry, ket 0. So the first one, first is control. Next is target. So 0 will not act on 0 because control is in the 0 state. So it comes out without any problem. So output is also 0 0. Next, I write here only. Next one. Next is 0 and 1. Control is 0. Target is 1. Of course, it won't act because control condition is very much valid even here also. So 1 also come out without any problem. So this state also remains as it is. Okay, next one, third part. Third part is 1 0 state. 1. This is 1. Okay, 1. And this is 0. Right. Now follow carefully. 1 is ready to act on Z. Why? Because it is control. Control, whenever it is in ket 1, it will act. It is ready to act and it is going to act on Z. But Z will not allow. Why, sir? Please recall Z gate. Z gate truth table you recall. In Z gate, it is 1 0 0 minus 1. Z gate transformation 1 0 0 minus 1. I think in my just previous video or previous to that I have explained this. In Z gate, 0 state will not change. It will come out without any problem. That means even though 1 is ready to act on Z, Z will not permit that 0 to change, so it 0 comes out as it is, 1 comes out as it is inevitably. Therefore, this state also not affected. Now comes the last one. If both are 1 1, what will happen? The last state. So 1. Now this control 1 will certainly act on Z. Now Z, whether it permits or not. See, in earlier two cases, control itself was not acting on Z. But in the third case, control is ready to act, but Z was not allowing because Z was in the 0 state. That's why I got back the same status. Now, control is ready to act, Z ready to respond. Control is ready to act, Z is ready to respond because in Z gate, ket1 changes to minus ket1. That is why it was called as a phase flip circuit. X is called bit flip. 0 becomes 1, 1 becomes 0. 1 becomes, 0 becomes 1, 1 becomes 0. 1 becomes 0, 0 becomes 1. Okay, that was bit flip. Now here 1 becomes 1 only, but negative sign comes into picture, the phase change will there. So Z is activated now. By whom it is activated? By this fellow it is activated. What type of action? Actually, if it is only control gate, bari control gate agididre, 1 would have become 0. 1 acts on 1 becomes 0. But it is not control gate, it is control not Z gate. Therefore, it becomes minus 1 ket, minus 1 ket. Therefore, the output is, here I write, it becomes, and of course 1 will come out without any problem, 1 with the negative sign. So this is input, this is output, that's all. That's all about the Z gate, control Z gate. So control Z gate symbol, control Z gate operations and truth table I explained. Next what? What I should write? Sir, you have to write the matrix form. Yes, I have to write the matrix form. As usual, UZ I write it as, and then first one no change 1 0 0 0, second one no change 0 1 0 0, third one no change 0 0 1 0, last one actually there is no change, but only thing is plus C is becoming minus, so you write minus sign here. Dear students, are you finding it very difficult? No, absolutely no. And even remembering this also is not a problem. Okay, so this is a matrix form of Z gate. Now I give you a task, or I will do one numerical and remaining you try. That means when UZ operates on 0 0, there will be no change. Prove that or show that. How to show that? UZ. As usual, UZ is 1 0 0 0. 0 1 0 0 0 0 1 0 0 0 0 minus 1 into my 0 0 is 1 0 0 0, and just you multiply 1 into 1 1, rest everything is 0. 0 into 1 0, rest everything is 0. 0 into rest everything is 0 and also 0. That means I generate 1 0 0 0. That means ket 0 0 only. So dear students, take this as an exercise. Show that UZ ket 0 1 is also not affected, but UZ ket 1 1 is affected. Show all these things. You can take it as exercise and do it. Okay. So I hope you are following all the gates. With this I have come to an end, almost an end of the gates. So I have the last gate which is called Toffoli gate. Shall I proceed? So that is for 3 qubit system. So we initially discussed about single qubit gates, that is Hadamard gate, S gate, T gate or XYZ gates. Then I started with multi-qubit 2-qubit system, CCNOT gate, and then swap gate, and then CCNOT Z gate. Now I come to the last part, that is 3-qubit system, which is nothing but Toffoli gate. So I take up the Toffoli gate now. See, even for Toffoli gate also I need CCNOT gate. CCNOT gate is one of the basic gate for multi-qubit system. So earlier I was talking about 2-qubit system. Now I will take 3-qubit system. 3-qubit means it will be having 3 zeros or 3 ones or 2 0 and 1 or 1 0 and 2 ones, like that. So I will write possible 3 states. First I write 0 0 0. This is the 3-qubit system. I think I mentioned this in the tensor product. What is the matrix form of 0 0 1? I write it here. How many elements should be there in the vector space? Yes, there must be 8. See, for ket 1 or ket 0 we have only 2 elements. For ket 1 we have 0 1, that is 2 elements. Like that, for ket 0 0 we have 4 elements. That's what we discussed just now. Like that, there must be 8 elements starting with 1, remaining all zeros. 3 4 5 6 7 8. 1 2 3 4 5 6 7 8. Okay, so this is 0 0 state. Okay, 000 state. Now Toffoli gate, how it works? In Toffoli gate, follow carefully. First two states are control and the last one is target. Remember, this is a 3-qubit system, therefore there must be 3 lines. 1 2 and 3 lines, right? So first one is control, so I write the dot here. Second one is also control, I write dot here. Third one is target, I write plus mark here. Okay, this is the Toffoli gate. So this will act on this, this will act on this, right? This is the circuit symbol. Now how it functions, how it works, that is very important. See, if the control is 0, it won't act. It won't act. This is a basic principle of CCNOT. Now I consider this state. All the 3 are zeros only. So this won't act, therefore this remains the same. So I have 0, 0 and 0. Therefore this 0 0 comes out without any variation. Correct? Now let us take up the next possible, that is 0 0 1. 0 0 1, what will happen? 0 0, the next one is 1. So this changes to 1. Let us see what happens. Sir, we know already what will happen. Because these two are zeros, there will be no action on the target, so it comes out without any problem. So it is also same. So therefore this is also unaffected. Next I take 0 1 0. What will happen? 0 1 0 0 1 0. Okay, first two I already told you are control, the last one only target. So 0 is in the control is in the 0 state. Even so therefore it won't act. One thing you should remember, only when both are in the active state, means only when both are ready to act, this gate will work. What I mean to say, if because of this 0 it won't act on this, but that doesn't mean that because this is 1 it acts on this. No, no, no. That is true only for CCNOT gate. When control is in ket 1, target changes from 0 to 1, 1 to 0. That is only for control NOT gate. This is control NOT gate. So it is CCNOT gate. This control is controlled by this fellow. Therefore it is double control gate. So therefore now also it remains 0 only. This comes out as 1 only. So no action. Therefore output is 0 1 0. Like that. 0 1 1. Now can you guess? Yes sir, it is again 0 1 1 only. It won't act at all. 0 1 1. When these two are not ready to act, 1 remains as it is. Next 1 0 0. What will happen? This is ready now. this is ready, but this is not ready. This is 1, this is 0. Anyway, this is ready, but it is not ready. Therefore, it comes out without any problem. Okay, so that means this remains as 1, 0, 0 only. Next possibility, 1, 0, 1. 1, 0, 1. How? Of course, 1, 0. This is 1. Now also, because these two are not ready means this may be ready, but this is not ready. Therefore, this is also not disturbed. So it remains as 1, 0, 1. So 1, 2, 3, 4, 5, 6. 2 more. Now let me try 1, 1, 0. 1, 1, 0. Now comes its action. Both are in one state. Definitely they will act. So definitely they will act. 1, 1 together acting on 0. 0 becomes 1. And this one comes out as it is. This one comes out as it is. So finally I have 1, 1, 1 output. Okay. And the last possibility 1, 1, 1. What will happen? 1, 1, 1. Whenever these two are in one state, then only my Toffoli gate is active. So 1 will now change to 0. So 1, 1, 1 becomes 1, 1, 0. This itself is the truth table. Just you remove this part you remove and write this is input and this is output. So input, output, this is a truth table. Okay, this is the Toffoli gate. Toffoli gate is nothing but double controlled NOT gate. NOT gate only, because finally it is acting like a flip. 1 becomes 0, 0 becomes 1. But only thing is, this is controlled by 2 control qubits. When it comes to vector representation, first 2 are control, the last one is target. Sorry sir, okay sir. Now how to write the matrix form? Yes, I will come to matrix form. Toffoli is equal to, come on tell me, what should be the dimension order of the matrix? It should be 8 by 8. Why? Because we are talking about 3 qubit system, so it should be 8 by 8. Like XYZ Hadamard or 2 by 2, CNOT and swap gate and CCNOT Z gate, they are 4 by 4. This must be 8 by 8. Sir, how to write, sir? Very simple. Write the column vector for all these states. Write the column vectors for all of them. I write it here. It may appear a little bit congested. Let me try. 1, 0, 0, 3, 4, 5, 6, 7, 8. First line. Second line. 0, 1, 0, 0, 0, 0, like this. Third one, generate third one, like this. Fourth one, generate fourth one. Fifth one, generate fifth one, like this. Sixth one, generate sixth one. Even seventh one, generate seventh one. And generate last one, 8th one. Dear students, I would like to mention one thing. In the notes link what I shared earlier, there was a mistake in the notes. So I corrected it and added the new link. Please download the notes using the present link. If you have already taken the printout of that previous link, just make the correction only in Toffoli matrix form. In the Toffoli matrix form, actually there was a mistake, so I corrected it. So this is just for your information. Now coming back to this, okay, I have written the matrix form, but this is not the transformation matrix for the Toffoli. So look at this. Up to 6th one, no change. Therefore, first line, second line, third column, 4th, 5th, 6th, no change. Only 7th and 8th you have to swap. 7th and 8th you have to swap. So this one goes here and this one comes here. So this way you have to swap. One goes here and this becomes 0 and this becomes 1, this becomes 0. So the last columns I just interchange. This is the matrix form of Toffoli gate. So I hope I explained all the concepts which are there in our VTU syllabus. Please go through all these things. Before I conclude, let me mention some drawbacks of the quantum computation. Quantum computation is not only having many advantages, but there are some disadvantages also. I just mentioned number one. Actually, quantum computers base our advantage is interaction of qubits. Okay, when two qubits interact, we get multi-qubit, that is 2-qubit system, or 3-qubit, 4-qubit, 5-qubit, like that. If you allow this interaction to happen, you will get too many interactions, 4 interaction, 5 interaction, etc., and it is very difficult to monitor the interaction. This is the first disadvantage. Second thing, see, these qubits are basically orientation of our electrons, either spin up or spin down, ground state or excited state, all these things. So these qubits are means these electrons are having the tendency to interact with the environment surrounding. If there is any unwanted magnetic field, while doing, for example, in your physics lab, while doing some experiments, if there is any magnetic field, unnecessary magnetic field, it will affect the deflections of the galvanometer or something like that. So similarly, even here also, qubits are having the tendency to interact with the environment. If that happens, we lose the information. So there is loss of information to the environment due to interaction with the environment. This we also call as decoherence. Decoherence is a major threat through the quantum computation. This decoherence will certainly occur, but we have to minimize it. Next, how long or in how many seconds or in how many minutes or in how many hours this decoherency happens. I just started the calculation, I switched on my computer. In how many hours this is going to have decoherency, so that I am going to lose the information. That time duration is known as decoherency time. So whatever the operation you want to do, you finish off within the decoherency time. For example, if your computer is going to be decoherent in half an hour, finish off everything within half an hour. This is another major problem in quantum computers. Next one, see, these quantum gates are there, no? As of now, they are basically made up of superconductors, and you all know superconductors work only at a low temperature. Therefore, quantum processes should be maintained at very low temperature. That is another problem. Okay, so like this we have some problems, but at the same time, and one more main thing, this is very important. See, in all these cases, we are finally depending upon alpha square plus beta square, that is equal to 1. What is this alpha and beta? Probability density. Probability amplitude square is probability density. So finally, whatever the answer we get is not exact answer, it is only probabilistic answer. That means output is only probabilistic. When we have probabilistic answer, to get the accurate answer, what we have to do? We have to do the operation several times. Multiple operations if you do, you get the exact answer. So initially output is probabilistic. To get the realistic and accurate, multiple operations, repeated operations are required. So these are the drawbacks. I have given the list here, please follow the list. Okay, this is about quantum computation. Dear students, I tried my level best from the video number 1 till this video to explain the fundamentals of quantum computation, physics involved in quantum computation, and essence of quantum computation. This is just beginning. This is just a drop in ocean. Okay, there is a long way to go. So I will try my level best to explain other higher level concepts also. But anyway, that is not there in your VTU syllabus. Just for the passion, just for the sake of understanding more about quantum computation, you can watch my subsequent videos also. See, some physicists are of pessimistic nature. Some of them are telling this quantum computer is not going to be realistic at all. It is not going to be, realized for common man level. It is only a sort of fiction. Some physicists are of this opinion. But some other physicists, some other scientists are very much optimistic, and they say quantum computers are not going to be realized not in next decade or following decade, within 3-4 years. So that is their optimistic level, and they are correct actually. And dear students, I tell you one thing, optimism is very important, because optimism makes things happen. Okay, I tell you, many major companies like IBM, right, they have already started working on quantum computers. They have invested billions of dollars on the research. Even our country also not lagging behind. I think I mentioned this in my first video. We have going for invest around 8,000 crores on quantum computation research. So this is a very hot favorite field, and this is a very promising field. Please try to pursue your higher studies in quantum computation. With this, I conclude my video. I am receiving a lot of positive comments, very good suggestions, and so much of encouragement I am getting. So please keep supporting me. I am going to come back with the remaining parts of the VTU physics syllabus. I may start with physics of animation. I will teach even superconductivity. For all the branches, I will try to give as much as possible from my side. I think this video is little bit lengthy. Please tolerate. Okay. So thank you, dear students. Thank you very much.